This video will be about proof by exhaustion. We've already covered proof by equivalence and proof by deduction. Now we're looking into proof by exhaustion. All right, so proof by exhaustion, you can also call it proof by cases, and that'll make sense in just a second, is just proving a statement by splitting up the cases into a finite amount and then verifying each case is true. So proof by exhaustion is just saying, all right, if I just split these up, can I list all the cases, list all the possibilities, and then prove that each one of those satisfies the claim. So real quick, I want to look at two kind of proofs next to each other, and then we can compare and contrast how a proof by exhaustion would be different than a proof by deduction. All right. So here it says, show that the difference of two consecutive square numbers between 25 and 100 are odd. Now, initially when I read this, I'm thinking, okay, show the difference. That seems like kind of a lot of work, but 25, it's only 25 and 100, between 25 and 100. We're only talking about square numbers. I might be able just to list all of these off, exhaust all the possibilities, and show that each one of them, the difference of two consecutive square numbers is in fact odd. So what I might do is I might just start listing all the squared numbers between 25 and 100, and here they are. And you're dealing with only 4 cases, right? So now it's simply, I can actually just go through each one of these differences and show that they're odd. So you would list this. There's that therefore symbol, therefore, right? And you just go through and you can literally each case, and your final statement is, hey, here are all my cases. So the difference of two consecutive squared numbers between 25 and 100 are odd. And you've gone through each case, right? 1, 2, 3. Now, what comes different is like if this were 25 and maybe 1,000, or 25 and maybe 100,000. Who knows, right? The bottom line is, if you can do it, you can just list off all of the cases. That's a proof by exhaustion. Pretty simple example. Now, to the right here, you'll see proof by deduction, kind of showing the similar proof, but this proof is saying show that the difference of two consecutive square numbers is always odd. So now we went from 25 to 100 to now showing that every difference of two consecutive square numbers is going to be odd. But we have to handle this differently because we can't exhaust. There are an infinite number of square numbers, so we can't exhaust. We cannot use proof. We can't use proof by exhaustion here because there's so many possibilities. So we have to be abstract here in our approach. So here's my proof. Let the numbers n and n plus 1, right? That's just a number and then the next number above it. But we are using abstract kind of terminology here, where n is a positive integer, and what we do is, of course, we can just start squaring n and n plus 1. So here I just squared n plus 1 because we're talking about the difference. So n plus 1 squared minus n squared, right? And now we're going to see, okay, what is this going to come to? Well, look at it over here on the right-hand side. You'll see that when you expand and then simplify, this simplifies to 2n plus 1. And remember, based on our definitions, that if something is equal to 2n plus 1, or some even product plus 1, this represents an odd number. So in fact, we have just proven that the difference of two consecutive square numbers is always odd. Look, since 2n is even, we know 2n is even, 2n plus 1 is odd. We know that. That was in our last, we covered that here, right? We can use these statements here. We know we can use these to prove things are true. So the difference of two square numbers is always odd. And please don't forget to always signify that you're done with the proof with the square box, QED, or that guy. All right. Now let's look at a little bit maybe more complicated approach. Example 2 says, given that n to the fifth minus n is equal to n minus 1 times n plus 1 times n squared plus 1, prove that n to the fifth minus n is divisible by 5 for all integers. All right, now you're like, what in the world? Where do I even start? And what I'm telling you right now is that you need to practice and read proofs. That is the way to get better, is by practicing and reading proofs. Because where do you even start here? All right. Well, if something is divisible by 5, again, it's always helpful just to have like some scratch work. And just write down facts. If something is divisible by 5, let's just say n is divisible by 5, n equals 5k. That's a statement right here where k is some integer. That's a statement that says n is always going to be divisible by 5. That's what divisibility means. That's how you represent divisibility in math. If you want to say a number is divisible by another number, you say n is equal to what? N is divisible by 10? Okay, n divisible by, right, like that, okay? All right, so you always have your scratch work working over here. Never think that proofs are just like written down first time. No, it's just like writing an essay. So when you think, okay, n has to be divisible by 5. So what we can say here, and here's this, okay. So what we can say is that if we divide n by 5, then the remainder is going to be 0, 1, 2, 3, or 4. What do I mean by that? Well, obviously, if you divide a number by 5, let's just say you divide 6 by 5, right? You would get 5. You would get 1 and 1/5. So the remainder would be, right, 1, right? 7 divided by 5, so that'd be 1 and 2/5. You get the point here? So these are the remainders. And so what we're doing is, we can look at all the remainders. We can say, let's just say that if it's divisible by 5, or if you divide something by 5, it's either going to be divisible by 5 perfectly, or it's going to have a remainder of 1, it's going to have a remainder of 2, a remainder of 3, or a remainder of 4. So really, we're turning this into a proof by exhaustion, because now we're listing out the possibilities of numbers when you divide them by 5. Okay? So these are cases. 1, 2, 3, 4, 5 cases. Now, we check for each case. So if we let capital N equal that entire statement, and if the first one we want to check is n equals, if n equals 5k, then you plug in 5k to each n. Plug in 5k to each n. You do this, and you end up getting that each term is divisible by 5. So, and of course you would show this. You wouldn't just, I know the book here doesn't show it, but you would show it. So that case, boom, we're good to go. Okay, we say, and so n is divisible by 5. Then you move on to the next case, all right? If n equals 5k plus 1, then the factor n minus 1, so this guy right here, you plug n, so 5k, if you were to plug in 5k plus 1 into n, right, the ones would cancel and you would just be left with 5k. Now you're like, well, how does that prove that it's divisible by 5? Well, because 5k is being multiplied by everything else here, right? And so again, the definition of something being divisible by 5 is if you can multiply if you can pull out a 5, right? That shows that it's divisible by 5. So this right here is divisible by 5. I know it seems like people are just like randomly saying things, but you can check their validity of their statements, okay? All right, so that's the second case. Boom. It's good. If n equals 5k plus 2, well, again, I just plug in 5k plus 2 to where n's to n. And again, my kind of goal here is to pull out a 5 at some point. Boom. Pulled out a 5. You see that my goal is to pull out a 5 because I'm trying to show that it's still divisible by 5. That case. Good. So I proved 3 cases. My next one is 5k plus 3. 5k plus 3, if n equals 5k plus 3, I plug that into n squared plus 1. Again, you're trying to get to a point where you can pull out a 5. There it is. Boom. And because we can pull out a 5, factor out a 5, that tells me that it's divisible by 5. So there's case 4. And the last case is 5k plus 4. Again, now you might be asking, okay, why did they plug this one into n plus 1, this one into n squared plus 1, this one into n squared plus 1, this one into n minus 1? Okay, again, they're showing you the final product. They're showing you the final product. They did scratch work over here, and they had to work this out to figure out that if I plug it in this term or I plug it in this term, then I can be able to factor out a 5. But they may have tried to plug, this guy into another term, and they couldn't factor out a 5. So they had to do their work to try and plug it into which term are they going to plug it into to see if they can factor out a 5. And as soon as you can factor out a 5, guys, then you can say that the big N, this entire thing here, is divisible by 5. Because everything's being multiplied. Remember, everything's being multiplied. So everything would be multiplied by a 5. And you see, okay, fifth case here, good. You can factor out a 5. Shows me this divisible by 5. Then my final statement is, in all cases, n is divisible by 5. So n to the fifth minus n is divisible by 5 for all numbers that are integers. Don't forget, end of your proof. I can't stress enough that you have to be creative to do these things, guys. You see the final product, but it took a lot of scratch work to get there. This is like your essay. This is like